So hello everyone, my name is Shishodia and along with me is Debarshi and this is our assignment for crypto tools. So coming to the first part of the crypto tool, let me first share my screen. So coming to the first part, which was the Caesar cipher. So basically, in Caesar cipher, we actually just shift the value. Like let's say if A is there and the key is 3, for example, here it is given. So it would be mapped to 3 and it would be mapped to D. So along with it, like from 0 to 25, these characters are mapped. And in any of this way, if we increase the key in integer, it would be obviously modulus 26. So it would be inside the characters only. So coming to the text here, as you can see, my input is given, and you can see the Caesar cipher box is also given, and text output is given. So when I actually try to run this, you will see that uh, it would be mapping to a word because our key is 3, so it has mapped to 3. And after that, if we try to copy this and we try to decrypt it, and we decrypt it using the Caesar analyzer and the frequency analyzer. First of all, let me explain you how is it happening. The input is going to the Caesar analyzer, and the input is also going to frequency analyzer, which is actually analyzing how many character or how what is the frequency of a particular character, and then it is then getting fed to Caesar analyzer. After that, the Caesar analyzer is giving input to the Caesar cipher, which is used for decryption because same way we have encrypted through the same algorithm, we are decrypting it through the same algorithm. After that, combining the text input, which is the cipher text, and the key, we actually try to decrypt the message. So when I will play this message, you will see that I would get the same answer as it was before. So from now I'm handing over to Debarshi.
So thank you, Urs, for explaining this in such a good way. Now I'll be continuing with the Caesar analysis once again. Let me just share my screen. Yeah. So again, coming back to the Caesar cipher, first I will give a brief demonstration. Caesar cipher is a very simple classical encryption algorithm. Like I have entered here a paragraph explaining cryptography along with my name and registration number. That's Debarshi Paul and registration number 2427. In the text input block, text is the plain text. We call this a plain text. I connected the input to in see the encryption component. This is the component that encrypts in the setting. Now I've used the key 3 here. So like it, what happens here is like A encrypts to D, B encrypts to F, B encrypts to E, and C encrypts to F. So that's how the ciphertext is formed here. That's the part. Now next, to decrypt this message, there's another part. Now the whole text that I've used here, I will copy, I have copied this and pasted it here. And here I've used two components, that's the Caesar analyzer and the frequency text. So what this does is the frequency analyzer used unigram values like E has the E, T, A appears most frequently in the English alphabets. So even after Caesar encryption, this becomes a fairly weak encryption algorithm because after decryption, we can see that we get by the plain text we have used before. Like cryptography is that the exact same thing we're getting with my name and the registration number. So using the ciphertext only attack, the analyzer guesses the most likely shift value. That is, we use 3 here. So that was fairly easy for crypto analyst to do. So this shows the Caesar cipher is insecure because frequency analysis usually refines the key. Now moving forward to the AES crypto part. Now, now I'll demonstrate AES encryption. AES is Advanced Encryption Standard. So it is widely used in Wi-Fi security, banking systems, secure file storage, etc. Now here, for input, I again use my registration number, and there are the plain text and the key. I have used Manipal Jaipur MUJ because it is a 128-bit key, and for now to show you the avalanche effect, I also need to use a 128-bit to make it fairly visible and understandable for you all. So let's play this. Yep. So this is ready. Now I'll be changing just one bit, the first bit of the AES round one. Yeah, just change the first bit. And now after the rounds, you can see that the values will change each round, round two, round three, round four. After 10 rounds, you can see the total change in the values is 48.4% from the original value that we were getting. So that is a huge change, we'd say. So like one change in the bit changes the whole ciphertext to by 50%. That's more than half. So if we observe this encryption is a pretty good encryption, we'll say. Even though after one digit, the output ciphertext changes almost completely. This demonstrates the avalanche effect very well. Good cryptography encryption, and this property of ACE makes it very secure. Now I will again hand over to Harsh, who will continue.
Thank you, Debarshi Paul, for your wonderful explanation. So I will be sharing my screen right now. Uh, so coming to the uh, another part, which is the EES encryption. So basically here I'm actually encrypting the message using AES algorithm. As you can see, my plain text is my registration number, and the key I have taken is the Manipal Jaipur MUJ for the 128 bit, as explained by Debarshi. So as you can see that when the it would be get encrypted, let me just play for it. It would get encrypted in this form. And coming to the avalanche effect, which actually says that even if one bit is changed, a lot more changes can happen in the ciphertext. So let me show you that. As you can see, like if I change, let's say 2 bits, for example, I change one and this. I'm changing this bits. So as you can see that after changing this bits, you can see that there is a lot more changes that is happening right now. So after round 10, you will see around 46.1 percent change in the whole thing from the original ciphertext. That means that this ciphertext, the change is from this ciphertext to another ciphertext is 46.1%. So coming to the RSA part, which is first we have to set up the RSA before encrypting it. So here I am taking the P and Q value for setting up before is P is equal to 251 and Q is equal to 79. And public exponent we have taken as 17. So you can take any prime value for this. I will run it actually to make you show that what are the public component. So as you can see, the 17 has come out to our public component and our private component is 18,353. And N, which is P into Q, is equal to 19,829. So we will be using this to actually encrypt and decrypt our message. So going as follows, you can see the public component and the modular n is given, and we are actually inputting it to the RSA algorithm. And as you can see, text input is also is given as my registration number certify this work. And I'm actually using the string decoder because it does not accept a string, it actually accepts the number. So when I will run this part, you could see that I have got some message ciphertext. And if I copy this ciphertext and go on to decrypt it, so basically I have to decrypt this message. So basically I would be pasting this whole ciphertext which showed before, and actually, as you can see, 18,353 is my private component and 19,000 is my modular n. And we are here using string decoder because it accepts a number only. So as you can see, my original text come out to be same as it was before the input. The input test was equal to the output. So handing over to Debashi Paul for further explanation.
Once again, thank you, Harsh, for explaining that in such a good manner. Let me share my screen once again. Yeah. Yeah. Now, again, coming back to the RSA key part. So, I'll be demonstrating RSA encryption once again. RSA, which is a asymmetric cryptography algorithm. Unlike AES, RSA uses two keys. That's the public key used for encryption and the private key that's used for decryption. So the first step in the RSA key is the key generation, where we use two prime numbers, that's P and Q, and the system then calculates the N part, that's the public exponent and the public modulus N. System calculates these values like 299 here, and also the private key 233, using the formula N equal to P into Q, and generates the sets of public and private keys. Now coming back to the RSA encryption, where I have entered my registration number and I registration number certify this work as the plain text. So this message becomes my plain text, and 17, that's the public modulus, and 299. So that goes into this string decoder and RSA. I have used string decoder for as with SK encoding, so that the text is not haphazard and we get a good hexadecimal output. So after the plain text goes into the component of RSA, we get a encrypted text. So it is we get this in hexadecimal order. Coming to the decryption part, the plain text is first converted again. So I've used ASCII encoding here again, and the RSA applies the encryption formula using the public key. So public key exponent I've used here. You can see that here it was 299, and I'm using the private key here as 233 of the receiver. So the result is again a numeric ciphertext that it was used here, and I get my original plaintext back using RSA. So RSA encryption ensures that the person with the public key only can decrypt the message. And RSA is currently is widely used in websites, digital signatures, etc. So moving forward to the password security part. Uh, in the final task here, I have analyzed password strength. Like CryptoTool includes a password strength analyzer, that's the component here. The tool measures password security using entropy, and entropy indicates how predictable a password is. So like I can text my registration number once again here, 2427030006, and play this once again. See, so the password has holds a value of 22 and the entropy of 2.23, which is a fairly low entropy because it contains only numbers and it is predictable and it is also short. But when I put a special character and along with it my name, that's Debarshi here. So it gives a factor of 100. The range is between 0 to 100 here, and 100 is the max. And it gives a very good entropy value too. So we can say that it cannot be broken using brute force attacks. Again, I can also show you like what are the weak passwords here, like 111111. It gives a value of 0. That's the lowest possible in the range. And it also gives an entropy value of 0. So this is a very weak value and can be easily broken using brute force attack. So, so high entropy means longer brute force attack time, making the password more secure. Like a tough password can take years to break using the brute force attack. Now I will be handing over again to Harsh, and he will be explaining the rest of the part.
Thank you, Debarshi Paul, for the wonderful explanation. Currently, I'm sharing my screen. Yeah. So coming to the password security part, which was there, actually, yeah. So basically, as you can see, the entropy is actually the randomness or the unpredictability of the string or the input or of the password as we are using. And strength is actually the resistant to the attack. Let's say if the strength is 100. So for here, crypto tool has a maximum of 100. So the strength, if it is 100, so it is more resistant to attack to a password which is of less value. And same goes for entropy. If entropy is high, so the unpredictability of the password becomes more high. And if less, then it is easily predictable. As you can see, my registration number is given as the input. And if I play, you can see that the strength is given as 21 and the entropy is 2.2, which is there. But if let's say I try to increase the strength and the entropy and I add a, a character, a special character and my name, you can see the strength has gone to 100 and the entropy has increased to 3.3. So it is much likely it is more resistant to attacks and the entropy has become high, so the predictability has also become very less. So this is our presentation for the crypto tool, and thank you. I would like to thank Uma Shankar sir for giving us this opportunity. I would also like to thank Tripti ma'am for giving us this opportunity to showcase our knowledge and our talent, and through tools such as crypto tool. And thank you. Thank you.